Okay, so thank you for your questions. Let's move on to the next speaker. The next speaker is Remi Blokker. And Remi Blokker is an electrical engineer by training, but now he is CEO of Bluerise. Bluerise is an ocean thermal energy company developing projects, providing technology. Remi, together with a number of other people, founded the company in 2010. We are very proud that we have that the company is based in our incubator. We have a new company incubator here at the campus, which is called Yes Delft, and Bluerise, Remi with his company Bluerise is part of it. Remi will now introduce to us the challenges and opportunities of ocean thermal energy conversion. Please have the floor, Remi.
Well, pleasure to see all of you here. A lot of familiar faces from the OTEC community that has been to the previous editions of the OTEC Symposium also. It's great to see all of you here. I want to start by giving my thanks to the team Delft for having us here and making this possible. And then also, of course, our sponsors, being DCNS, Deltares. Deltares is hosting tonight's event with a tour of the facilities and a dinner. I would like to thank Akko Energy, working with DCNS on the Martinique project, Technip, also active in developing OTEC systems, a newcomer, Bardo Ocean, just recently announced their first project in the Maldives, and another newcomer from the Netherlands, Artec, is also present here. So let's give a big hand to all these sponsors. Ocean thermal energy. Why? Well, because the oceans are the largest solar collector and energy storage in the world. And the good thing is that they're already here and paid for. Ocean thermal energy is the biggest of all ocean energies when you look at the potential that they offer. This is a sort of exaggerated picture of a coastline, a tropical coastline, where you see some nice palm trees, and a hotel and some other buildings. And the characteristic of the ocean is that the top layers are very warm and the deep layers are very cold. You can actually think as the ocean as a large battery of stored thermal energy. You can use this thermal energy onshore by installing a pipeline that draws up the cold water to the shoreline. And then actually the most obvious application of all is not really OTEC, but it's actually cooling. Cooling of buildings, saving 90% of the energy required for cooling. And as Cornelis already mentioned earlier, that energy saving, energy conservation is a big thing. This is seawater air conditioning, SWAC, cooling. The other thing obviously is OTEC, which is producing electricity using the temperature difference between the warm surface layer and the cold seawater, as we all know. And then some other applications, such as the production of drinking water and all sorts of byproducts, such as agriculture, aquaculture. I think most of you are familiar with all of this. So it's not just that the ocean provides electricity, they also provide a lot of other benefits. This is all onshore. The big application for OTEC is obviously offshore in large floating platforms. A little movie. Oh, it's nice to get that going. Oh, no. It's the working principle, but the introductory movie already showed how the OTEC cycle works, and I bet you that most of you here already know it, so I'm just going to skip it. A little bit about what we do. We do basically three things. Project development, that's, I would say, our largest activity at the moment, trying to get this going. The other large thing obviously is technology development and software development. The focus that we have is really to push down the levelized cost of energy, so trying to get the most kilowatt hours out of the least amount of money. OTEC offers a lot of opportunities. First one is a baseload energy source. Cornelis already mentioned that that's essential because intermittent resources can only bring us up to a certain percentage. Do we want to go for large amounts of renewable energy? We need other alternatives. I think later today we have some other excellent presentations on this by one of our colleagues who will make it, who is a number cruncher and who will show you what the effects are of having a lot of intermittent resources on an island. Other benefits is there's hardly any land requirements, so an OTEC system doesn't use a lot of square meters, particularly small islands. The target market are very land constrained. You don't have a lot of land available, and the land that you have available, especially on the coastline, is high value property. So you want to use as little as possible. OTEC has no visual impact. Maybe interesting to mention that Aruba has a very ambitious renewable energy goal, but they're hindered by the fact that the wind park that they are now developing is blocked by the community because it's in a nice location and people just don't like the view of windmills. Personally, I like windmills a lot, but a lot of people don't. And then you have a lot of byproducts when you produce OTEC. OTEC is a baseload energy source because the ocean temperatures are very stable, and I have some examples of that on the next slide. It's very easy to integrate technology because it uses rotating equipment like traditional generation that provides a good power factor. No backup is required, and given the right PPA conditions, OTEC could even be considered to be dispatchable. Let's compare OTEC with some other renewable energies. This is a typical weekly production curve of a wind park in the Caribbean. People in the Caribbean always say that their winds are extremely stable, which I think, relatively speaking, they are, but since wind energy is wind speed to the cube, you see that the actual output of a wind park, even under these conditions, is very variable, very intermittent. So it's not a reliable source of energy. On the other hand, in the picture next to it, you see a Facebook posting of the Okinawa OTEC plant. This was last January when it snowed in Okinawa. This is very rare. Happens only once in 40 years, I think. But what they mentioned is that even in the winter, with snow, it still produced baseload energy 24/7 because the ocean temperatures are very stable. I also want to highlight another comparison, that's with solar PV. Solar PV prices are going down fast. What this here shows is the cost price build-up of a solar PV farm, a 100 megawatt farm done by NREL of the US. And what you can see is that about 30% of the cost is the actual module, and the rest is development cost, land use, EPC work, well, basically all the other stuff that you need to build a solar PV farm. OTEC also has a similar cost structure, but for OTEC it's not so much the module, but it's the heat exchanger that drives the cost. That's the main cost driver. So what we did here is compare a solar PV module with an OTEC heat exchanger. A solar PV panel produces about 440 kilowatt hours per square meter per year in a very sunny place, so for instance in the Caribbean. A solar PV module is a very complex silicon module that is quite costly to manufacture, but still, you know, recent recent prices are going down fast to what Cornelis also mentioned, I think 3 or 4 cents a kilowatt hour. Now compare that to the main cost driver of OTEC, which is the heat exchanger. The heat exchangers are built up either using plates or tubes that are very thin. So in this example, this is a metal plate 0.6 millimeter thick. And an annual production of a heat exchanger in electricity units is 800 kilowatt hours per square meter. So it's almost double that of a solar panel. And you can see that inherently the cost is lower than that of a solar PV panel because a 0.6 millimeter metal plate is always cheaper than a solar PV module. Some more comparisons. Wind and solar with OTEC. So a 10 megawatt OTEC system delivers about 75 gigawatt hours per year. For that same amount of energy, you need 50 megawatt installed capacity of solar and about 25 megawatt of wind in good locations. This is not everywhere, but if you have sunny locations or windy place, this is what you need. The reason being, OTEC is a base load, so 24/7, solar and wind are intermittent and don't produce when the sun doesn't shine or the wind doesn't blow. Another big difference is the land requirement. For a 10 megawatt OTEC, you need about 500 meters, maybe that's even too much. It's just the station that you need to place the transformer and the connection to the OTEC system. A solar PV farm generating the same amount of energy requires 2.5 million square meters. A wind park, 800,000 square meters. So that's a lot. I also put it in a visual. You can see on the left the capacity requirements, and on the right you see the land requirements. OTEC nothing, solar huge, wind also pretty big. So, and these are items that people often overlook. We often get the question, what's the price of OTEC per megawatt? Well, you cannot compare megawatts installed capacity because that's apples and oranges. You need to compare energy production. And you also need to take into account the value of having a baseload. So it's a difficult comparison. Byproducts are also very interesting aspect of OTEC. Cooling I mentioned, aquaculture and agriculture, and drinking water production. All very valuable byproducts for island nations that are dependent on import of not just the energy but also foods and that often produce their water with energy intensive reverse osmosis. So valuable byproducts. And as an example, this is a project that we are developing in Curaçao, the Ocean Eco Park, that consists of basically all of these items. Inspired, I must say, by places like Nelha and also Kumajima, where similar areas exist. The Ministry of Economic Affairs of Curaçao did an economic analysis, and what they came up with is that this project will add about 1% to the GDP and over 900 jobs. It will save about 7 million in energy a year and a reduction of 14,000 tons of CO2. So it's quite a, for that local economy, it's quite a big thing. But obviously there are challenges, and I think the number one challenge is the fact that OTEC is too expensive. But that's also a myth. It's the number one myth that surrounds OTEC. Because similar as offshore wind, and Cornelis also mentioned it in his presentation, that same myth surrounded offshore wind. Offshore wind was too expensive, windmills only run on subsidy, but the recent tender of the Borssele 1 project drove the price down to $72 a megawatt hour, or about 8 US cents a kilowatt hour, which I would consider to be a highly competitive price already. And it can go down even further. And that's because all these technologies, be it energy, but also iPhones, cars, basically any technology goes through a learning curve in which the price reduces if you just produce more. And OTEC will see the same thing. This is how we forecast OTEC to develop. So on the horizontal axis you see the total installed capacity of OTEC, and on the vertical axis you see the levelized cost of energy in US dollar cents. And our expectation is that once we reach the 50 megawatt point, so that's after the first few, say, government-funded OTEC systems are live, prices will start going down from 20 cents, and by the time we've installed, say, half a gigawatt, already almost at 10 cents. And then going further down, and we expect ultimately the price to reach about 5 cents a kilowatt hour. And it's a baseload source. So how do we make it all happen? I think two things are already happening today. And the first is that governments around the world are funding OTEC development. So the examples are obviously Hawaii, Korea, and Japan that have small pilot systems already operational. These pilot systems prove out the fact that OTEC practice matches the theory, and so I think they are a highly valuable way of demonstrating that the theory works. And obviously the Martinique plan that DCNS is working on, funded by the European Investment Bank, is also going to be a very, that's going to be a big milestone for the OTEC industry. So government funding is one way to drive down costs and to get the TRL levels up to a level that also private investors would invest. But the other way of getting there, and that's also our approach, is to use the synergetic use of the seawater and combine a smaller OTEC system with a large district cooling system. Curaçao is an example, but also the recently announced project by Bordeaux is similar in nature. But what we also hope is that there will come multilateral support for the development of OTEC. And I just came back from the CREF, the Caribbean Renewable Energy Conference in Miami, and most Caribbean islands are shouting out for institutes to help them develop this resource, because it's really their resource. It's what they want. There's ministers of energy that are asking for support. These islands are too small to establish, a TU Delft or a CRISO or one of these bigger research institutes. So they need help from us and from the multilaterals. So I think we as an industry need to work together and step it up. So I think that's the main challenge. Other challenges are obviously we need to make sure that we don't cause any environmental impact. Studies are positive, but obviously the proof of the pudding is in the eating. So we need to deploy systems and actually measure the environmental impacts. And then I think the last challenge that we identified is that we really need to work together as an industry and to make this a collaborative effort. And therefore it's good to have you all here. And I hope you all enjoy the conference. Thank you.
So thank you, Remi. Are there questions, additions, suggestions? Yes, please.
Thank you, Remi, for your excellent presentation. I have two questions. May I refer to your proposed OTEC project in Curaçao?
Sure.
First, whether EIA idea has been completed or being done? Second, when you expect the first project to be commissioned?
That's a very good question. It's a question that we ask ourselves also a lot. Obviously, it's a large project. Large projects you have to do with a lot of stakeholders. And you were asking if what is complete?
When you expect?
Yeah, so we hope to break ground next year and to have it, construction time is about a year, and to have first customers receive cooling a year later. Thank you.
More questions? Okay, then thank you once more for this very good introduction. So we are nearing the coffee break, but the idea, Berend, tell me, that we will have a small quiz. And it's not